to have Chandan again. So he'll be talking this time about the reconstruction arithmetic circuits, and he's going to talk to us about the average case complexity of this problem. Yeah. Okay, Chandan.
Okay. Yeah. Thanks, Kevi. Hi, everyone, and welcome to the second talk on arithmetic circuit reconstruction. And as Kevi just said, today we'll focus on average case reconstruction. Let's start by recapping the definition of the reconstruction problem. Recall that we are given black box access to an n-variate polynomial of degree d with the promise that it can be computed by a circuit of size s, and we have to output a small circuit computing the same polynomial f. Right, and three desirable properties of reconstructions are the output circuit should have small size, ideally poly s, and ideally we should do proper learning. That means that the output circuit should also belong to the same class as the input circuit C, and the algorithm should be efficient. It means that it should have time complexity polynomial in the parameters, the usual parameters, variables, degree, and size. All right, and what we did in part one is we did some kind of a brief survey of known results on worst case complexity, and then saw a little bit of details of sparse polynomial interpolation, which is depth 2 circuit construction. And then we saw a couple of algorithms for reconstructing depth 3 powering circuit. One was improper, and the other one was proper, but for constant top fanning depth 3 powering circuit. The improper one outputs a circuit which is basically a read once oblivious algebraic branching program. All right, so today we're going to focus on average case reconstruction, which is also known as, in the community, it's also known as learning in the non-degenerate case. Right, so let's begin from where we left. We were discussing proper learning of depth 3 powering circuit, and recall a depth 3 powering circuit computes a sum of powers of affine forms, or degree 1 polynomials. And we want to output some small circuit computing the same f. And as we saw in the last talk, that worst case learning of depth 3 powering circuit seems hard because Wording rank is hard to compute. But what about average case learning? By that, we mean what if the coefficients of the LIs are chosen randomly, and that f is given as input. We have black box access to such an average case f, where the coefficients of the linear forms are chosen randomly. Right. So to make it a little more formal, let me define a random.
Chandan, one question. When you say random here, these are from where? Oh, from the field. Yeah? There is an underlying field that you're fixed.
Right. So I'm just sorry. I just defined it here.
Okay.
That let's define a random depth 3 powering circuit by choosing the coefficients of these linear forms uniformly and independently at random from some sufficiently large finite subset of the underlying field, right? And that's my input, and we would like to construct a circuit computing the same f. But this time, let me define the problem as a proper learning problem. This time, I want to output a small depth 3 powering circuit for f. Otherwise, it doesn't make that much sense, because you already have for the average case. Just for notational simplicity. Yeah, sorry.
No, we lost you when you were reading the last. Lost your voice. You were.
Yeah, somehow I don't know, my connection is a bit unstable. Yeah. So just for notational simplicity, let me assume that the degrees here, d1 through ds, are all the same, d, right? And the affine forms L1 through Ls are actually linear forms. There are no constant terms involved here. These are just for simplicity. None of these assumptions are that much needed.
So,
and let's
so
ask, what's the complexity of this?
So when you say that the black box
yes,
access, it's to a random sigma power sigma circuit computing f. So that means f, you can think of f as not being fixed, is it? And as you make queries, f.
Right. So I think of f as, someone chose these LIs randomly and then gave f as a black box to my algorithm. And the question is, can I reconstruct a circuit for f? And if so, with what probability? And now the probability would be on the input distribution, right?
Okay.
So I'm just choosing the input from a distribution and hoping that with high probability on the input distribution, the algorithm would be able to construct a circuit for a depth powering circuit for f.
We want to say that for many such f's,
yeah. So for exactly, for most such f's, we should be able to reconstruct or give a witness depth powering circuit for f. Yeah, you're right. Yeah. Okay. Right. So let's ask, what's the complexity of the problem, and or whether or not we can indeed reconstruct and give proper learning algorithms for most f. Right. So let's handle an easier case first, right? And even that easier case is important in its own right. And so let's suppose that S, the top fan in S here, is less than or equal to n. Right? And notice that what this is saying is, let's say S is equal to n, right? What this is saying is you have n linear forms in n variables, right? And you're choosing the coefficients of the linear forms randomly. Now, it's not too hard to see that if you choose the n coefficients of n linear forms randomly, then these linear forms would be linearly independent with high probability, right? So these are basically n vectors. You're choosing the entries randomly, right? So and in this case, we say that f is equivalent to the dth power symmetry polynomial in S variables, right? So let me explain the term in more details. What do I mean by f being equivalent to a power symmetry polynomials? So let me take a small detour and go into what is called the polynomial equivalence problem. Right, keeping this special cases in mind that S is now upper bounded by n. Right, so what's the polynomial equivalence problem? Let us define orbit of a polynomial first. The orbit of an n-variate polynomial G is the set of polynomials that can be obtained by applying invertible linear transformations on G. It's Gx, where A is an invertible. And we say two polynomials f and g are equivalent if they lie in the orbit of each other. This is an equivalence relationship. If g lies in the orbit of f, then f also lies in the orbit of g. Right? And we say that they're equivalent, and I'm going to denote this relation by this curve. Okay, so notice one thing, and this is what I meant in the last slide, that if L1 through Ln are linearly independent, then f is equivalent to the power symmetric polynomial, which is defined as just x1 power d plus x2 power d to xn power d. Yeah, because an invertible linear transformation is just replacing each variable by a linear form, and these linear forms are linearly independent. Right? So it's a very special case, and we are asking whether we can learn our circuit or learn the LIs in this special case. Right. So what is known about the equivalence problem? But before that, what is the equivalence problem? The equivalence or the polynomial equivalence problem is the following: you're given f and g verbosely as lists of coefficients. Right? No more black boxes. We'll go back to black boxes in a while. But classically, the polynomial equivalence problem is defined like this: and you want to check whether indeed f and g are equivalent or not. And if so, then you would like to output a witness A that indeed f is equal to Gax. right? And this problem has been studied intensely, just like the graph isomorphism problem. This problem has also been studied intensely, well, not as intensely as maybe GI, but still we know quite a bit about this. For example, we know that the polynomial equivalence problem over finite fields lies in NP intersection coem, and that means that it's unlikely to be NP complex, right? It is not unless space collapses, right? So it seems like it is not too hard, at least not over finite fields, but it's also field dependent. It's not known, whether the problem is even decidable over Q, right? And for arbitrary fields, the best known complexity of this problem is the same as polynomial solvability. And polynomial solvability is kind of a hard problem. For over finite fields, the best complexity is like double exponential and so on. But at least exponential in over other fields like reals and complex numbers. And the way polynomial equivalence problem reduces to polynomial solvability is a very trivial way. You just treat the entries of a witness A as variables, then you substitute in G, and you equate the coefficients of F and G, and that these will give you equations, polynomial equations, where the variables are the entries of A, right? And you solve for such A, right? So and now the problem is in the general case it's not clear what's the status, whether we can do anything better. So let's ask whether we can solve this problem efficiently for restricted classes or families of polynomials, right? So one such very natural and restricted class is quadratic forms, where both F and G are degree 2 polynomials and they're homogeneous. Let's say, well, homogeneity is not quite required, but let's say they are, right? So and we know more or less a complete solution for quadratic form equivalence. We know how to solve them in randomized polynomial time over finite fields, complex numbers, reals, and rationals with access to integer factoring oracle, right? So, and the randomization part is not quite required. It's only required over finite fields, but over complex numbers, reals, we can actually do it deterministically. And at the heart of this, the algorithms that go behind quadratic form equivalence is some well-known classification results for quadratic forms. By a classification result, I mean a result of this kind. I stated at the last line that over complex numbers, we know that any quadratic form that has n essential variables is equivalent to the power symmetric polynomial x1 squared plus x2 squared to xn squared. So any quadratic form with n essential variables, you can bring it to this form, right? And if someone tells you this, this canonical form and this classification result, then checking whether two quadratic forms over C are equivalent or not is just checking whether they have the same number of essential variables or not, right? And which is fairly easy. We saw one such algorithm, or at least we stated it in the last part, right? You just have to take derivatives and see whether the dimension is of the space of first order derivatives is n or not, right? So and if one works a little harder, one actually can also find the witness A and not just check equivalence, right? And so, and that's how quadratic form equivalence becomes easy. But the problem quickly becomes hard again, right? If you go from degree 2 to degree 3, then there are indications that it is hard, right? For example, we know that cubic form equivalence is graph isomorphism hard, and if that doesn't convince you, that it is hard, because we now know of efficient algorithms for graph isomorphism, there are results which suggest that it is possibly harder than GI. For example, we, due to recent works by Groschow and Xiao that built on several other earlier works, they showed that a bunch of problems are actually polynomial time Turing reducible to each other, right? These are tensor isomorphism problem, problems called matrix space isometry and matrix space conjugacy, algebra isomorphism, cubic form equivalent. They're all polytime equivalent to each other, which we don't know efficient solutions to any of these problems. And there are indications that probably these are may not admit polynomial algorithms. All right, so what do we do? Like the problem becomes hard again if we increase the degree, right? So Kayal introduced a line of study for equivalence tests, a very natural variant of the polynomial equivalence problem, where G, or one of the polynomial, comes from some well-known polynomial family. What's a polynomial family? A polynomial family is a collection of polynomials, let's say GM, where the polynomials are indexed by integers, natural numbers, and you can think of determinant being a polynomial family. Right? For every n, you get an n by n determinant, right? And this variant of the polynomial equivalence problem is defined like this. This time, I give you black box access to F. Right? I'm doing this deliberately because looking ahead, we know of efficient solutions for several well-known polynomial families where we are given only black box access to it. So that's why I'm defining the problems also with black box access to it, because we can do it, we can solve it. So let me define it like this: given black box access to F, check if F is in the orbit of some GM, right? Where GM is taken from this, some polynomial family G. If yes, then you output a certificate A, right? So that's a problem. But why should it be interesting? Why is this version of polynomial equivalence interesting, right? So it is natural. So it's a natural problem to study. So that's one reason it is interesting. But it is also interesting from the viewpoint of learning general circuits. So let's see why, and by first defining what are called affine projections. I'm sure you have seen it in some of the earlier lectures. So let me define it anyway. The set of affine projections of an n-variate polynomial G is the set of all polynomials that can be obtained by applying linear maps on the variables, right, along with the translation vector B. And these linear maps A need not be invertible anymore. These are some matrix, n by n matrix A. Right? These are affine projections of A. And why are they interesting? Because they're interesting, especially for several well-known polynomial families, because of known results, which are not too hard to see. That affine projections of, let's say, the power symmetric polynomial, which we just defined as x1 power d plus x2 power d. If you replace the xi's by arbitrary linear forms or affine forms, that captures depth-3 powering circuits, right? Any depth-3 powering circuit is in the affine projection of the power symmetric polynomial. Similarly, any depth-3 circuit is in the affine projections of what is called the sum product polynomial. We are going to define this polynomial in a few minutes. The sum product polynomial is basically sums of monomials, and these monomials are in disjoint sets of variables. Right? If you replace the variables by arbitrary affine forms, you get general depth-3 circuits. Yeah, and by the very definition, sum product polynomial is Reed-Wahn's formula, and so on. So we'll come to it. But point is, similarly, there are other polynomials like alternating normal forms, determinant, IMM, whose affine projections are immensely powerful. So if you think of the corresponding learning problem, that if I want to check whether F is in the affine projections of let's say a small IMM or not, that's like checking whether F has a small ABP or not, right? So that's as hard as a general case. So with this in mind, like, it becomes natural to first ask this question, like, what if in this problem, if I make A invertible, right? A an invertible matrix instead of a general affine transformation, right? So, and that's exactly the polynomial equivalence problem with respect to polynomial class G. But there's another interesting reason. The set of affine projection is not much larger than the orbit of G, or the affine projections of G is not much larger than the orbit of G, right? Because if you take the closure, by closure, I mean you think of the polynomials, the coefficient vectors of the polynomials in the orbit of G as points, right? And if you close them, right, in what sense? You think of the smallest variety containing these points, that set is the orbit closure, also known as the Zariski closure of the orbit, right? So it's basically that affine projections of G is sandwiched between the orbit of G and the orbit closure of G. So it's not much larger in that sense, right? So sorry, like I'm just trying to create the polynomial equivalence problem for well-known circuits. No, that's why it becomes natural to study this question. All right, so sorry, just to check, am I still audible?
Yes, yes, yes.
Okay, right. So, and indeed, people have studied polynomial equivalence problem for several well-known polynomial families like determinant, permanent, IMM, and there's another version of IMM called trace IMM, elementary symmetric polynomials, power symmetric polynomials, sum product polynomials, and some others. Right? And for all of them, when we now know of randomized polytime algorithms, given black box access to F. The polynomial that is relevant for our discussion is the power symmetric polynomial. So let's get into that. And let me define again. The power symmetric polynomial is the sum of the dth powers of the xi's, right? And let's see an algorithm, a fairly nice algorithm for polynomial equivalence for power symmetric polynomial. And let's assume that the degree is greater than 3, greater than equal to 3. Why? Because when degree becomes 2, then it is basically the quadratic form equivalence question. And we just saw like that any quadratic form over C is essentially equivalent to the second power symmetric polynomial. So let's forget d equals 2 and think of only d equals 3. So we are given F, which is a sum of L linear forms power raised to the D, right? And the LIs are F linearly independent. Yeah, so we do a little bit of pre-processing first. And yeah, of course, the question is, can we recover these linear forms? And note one thing, we can only recover these linear forms up to dth roots of unity, right? Because if L1 is a solution, then if you multiply L1 by a dth root of unity and raise it to the power D, then you still get L1 power D. So we can hope to recover the LIs only up to dth powers. They're not unique in that sense. Yeah, so the pre-processing is you first notice that the number of essential variables of F is S, exactly S. That's because F is in the orbit of the power symmetric polynomial. So it is obtained by applying an invertible map. And invertible maps don't change the number of essential variables. The number of essential variables of the power symmetric polynomial is exactly S. So this is also S. So what you can do is you can apply this, this Karlini-Kayal algorithm to remove redundant variables. And without loss of generality, you can assume henceforth that S and N are the same. Right? So it becomes easier for me to make it precise. So from now on, I'll assume S and N are the same. And the problem is the following. You're given black box access to F, which is in the orbit of a power symmetry polynomial. And you want to output a matrix A such that F is equal to P sim AX. The algorithm uses what is called the Haitian matrix of F. Yeah, so let me define what's the Haitian of F. So I'm going to denote by this notation the derivative of F with respect to the ith variable and the jth variable. And the Haitian matrix is a square matrix. It's an n by n matrix whose ijth entry is the derivative of F with respect to the ith variable and the jth variable. Right? It's easy to see it's a symmetric matrix, right? And the Haitian appears very naturally for it in Taylor expansions of multivariate polynomials, and that's how they play a crucial role in finding critical points like second derivative tests and also optimization problems over reals, right? So, but the property of Haitian that we're going to need is not the Taylor expansion. The property of the Haitian that we're going to need is given in this observation, right? We will see how the Haitian of F and G are related, where F is in the orbit of G, let's say. And it's a very nice, neat relationship, which is basically chain rule. that the two Haitians, the Haitian of G evaluated at AX. So this notation means I first do the Haitian of G, and then I apply the transformation A on it, right? So the Haitian of G evaluated at AX, that relates to the Haitian of F via a congruence, this congruence relationship, right? It's A transpose. Right? And the proof, I'm not going into it, it's basically chain rule, how the gradient of F and the gradient of G are related to each other, right? If you just use chain rule of derivatives, you get this, right? So simple exercise. But the nice thing is, now if you take the determinant of the Haitians, both sides, what you get is that the two determinants are very nicely related, right? Haitian, the determinant of the Haitian of F is some non-zero constant times the Haitian of the determinant of the Haitian of G evaluated at AX, right? So we're going to use this relationship. So let's record this relationship in this box, that Haitian of F and the Haitian of the power symmetry polynomial are related like this, right? And especially the determinant, we will need the relationship between the determinant. And let's now give the algorithm. The algorithm, at first, it computes black box access to the determinant of the Haitian of F. Remember, F is given as a black box. So at first, I want to compute the Haitian of F, right? And the claim is we can compute black box access to the Haitian matrix of F easily, because the order of the derivatives involved is only 2, right? And one can get black box access. Let's say, just to give you an example, let's say I'm given black box access to F. I want black box access to the derivative of F with respect to some specific variable X. What I do is I pretend that F is a univariate polynomial in the X variable, whose coefficients are polynomials in the remaining variables. So you first interpolate these coefficients, right? You can just plug in different values in place of the X variable and interpolate, and the coefficients. And once you get black box access to these coefficients, getting black box access to the derivative is not an issue. You just have to multiply the coefficients with appropriate powers of X and scale them, right? And what this means is, given black box access to F, I can get black box access to any constant order derivative of F, right? But going beyond constant order is not allowed. And fortunately, Haitian involves only constant order derivatives, so we can compute the Haitian matrix as a black box, and from which we can also compute its determinant as a black box, because determinant is easy to compute. All right. So once we get black box access to this determinant, which is a polynomial, we compute black box access to all the factors of this, all the irreducible factors of each, right? And it is here where we use Kaltofen-Traeger's black box factorization algorithm. And finally, in the third step, we recover A by looking at the factors of each, right? And so let me argue the correctness. The first two steps are obvious. So this is what you do. So the correctness basically lies in the third step. So we have to argue the correctness of the third step. So let's see why the algorithm works. So let me write the third step here. Let's just first see how Haitian of the power symmetry polynomial looks like. It is just the second order derivatives, right? So in the power symmetry polynomial is the sum of these powers of variables. So if you take the second order derivatives, you basically get a diagonal matrix whose diagonal entries are x1 power d minus 2 to xn power d minus 2 scaled by some non-zero constant. All right. So if this is the Haitian, now we can use this relationship recorded here in the box and see that the Haitian of the power symmetry polynomial evaluated at AX is basically the same matrix with the variables replaced by the appropriate linear forms, right? Where AX is this column vector of linear forms. All right. So now if you take the determinant of the Haitian of the power symmetry polynomial, it becomes essentially the determinant of the Haitian of F, which is capital H. So you get constant times the product of the diagonal entries. So, and this is very nice, that this means that the black box is actually a polynomial which factorizes completely into linear factors or powers of linear factors. So if you get access to these linear factors, then we are done, right? So what you do is you recover these linear factors, but we can only recover them up to F multiples, right? Because I'm applying a black box factorization algorithm, and it can't find the linear forms uniquely, because if L1 is a factor, a constant times L1 is also a factor. So I recover them up to F multiples. I call these whatever linear forms we have recovered, I call these L1 prime to Ln prime, right? So they are constant multiples of corresponding LIs. Fine. And finally, how do you get the LIs? You do this. So notice one thing, that now my algorithm knows the L1 primes, right? And I know my F, input F, can be written as some constant Z1 through Zn times these linear forms. Why? Because L1 prime is just a constant times L1. Similarly, Ln prime is just a constant time Ln. Yeah, so I know that this is true. So I just have to find the Zs, right? So I do this by solving a linear system by pretending that the Zs are the variables, Z1 through Zn. Right? I evaluate the linear forms L1 prime to Ln prime at n random points, right? And this evaluation, and also I evaluate F at those corresponding random points, and this will give me a linear system in just the Z variables. And then I solve that linear system. And this works because L1 per D, L1 through Ln are sort of F linearly independent. So if you evaluate them at n random points, the corresponding coefficient matrix that you get, that is invertible also with high probability, right? So we saw something like this in the last lecture, where F linearly independent polynomials, if you evaluate them at random points, the corresponding matrix becomes full rank, right? So, and that's it. That's the correctness of the algorithm, right? So yeah. So before going into that, let me ask, like, any questions till this point?
Yeah, I mean, I'm a bit confused. So when you said I want to get hold of the derivatives, these are the derivatives evaluated at some input that you give, right, to the or because finally I'm a bit confused about the way you use it. The way you use it is you are thinking of the Hessian now as a polynomial, the final Hessian, isn't it?
Right.
But when you are given
exactly.
black box access, you can only ask, can you give me the Hessian? Can you give me the value of the function at these points? I mean, I'll give you some actual honest complex numbers or something, right? But you're saying by interpolation, you can actually reconstruct the polynomial itself. Is that what part?
Right. So yeah. So as you said, like, let's think of this. Like, let's say I want black box access to H, which is the determinant of the Hessian of that. Right. That means I'm given a point. I want to know what's the value of H. H is a polynomial. What's the value of H at that point? Right.
Correct.
So if I know what's the value of the Hessian of F at that point, then I just have to compute the determinant, and I'll be done. Right. So the problem now reduces to finding the value of the Hessian of any entry of the Hessian matrix at a given point. Right. So now let's say point is given to me, and all I have is black box access to F. Right. So from black box access to F, what I'm saying is let's think of slightly the easier problem. Let's say, how do I get black box access to a first order derivative, right? I want to evaluate
2 points, right? You can evaluate at 2 points and divide by H or whatever, and then you'll get the, isn't it? I mean, this is what confuses me. So if I look at f of x plus h minus f of x divided by h, that is really the derivative. I mean, of, say, take one variable and just add some epsilon to it, and f of xi plus h minus f of xi divided by h should give me the derivative at xi in the direction x. Correct?
Exactly. Exactly. Yeah. So because we are doing it over arbitrary fields, that's why I said you can interpolate. But what you are saying is essentially that. So you can actually translate that one single variable and get black box access to its derivative.
But what confuses me is eventually you want to write it as a polynomial, is it? I mean, I'm a bit confused about because when
eventually I don't want to write Right. I don't want to write H as a polynomial. What I want is I want black box access to H. From that, I will get black box access to its factors. Once I get black box access to its factors, then I will reconstruct the factors.
Okay,
right?
okay.
Correct.
Now
The
in the
factors are very
last
simple.
step. Okay, okay. Those LIs
In the
are
last
being
step,
used
yes.
by. Okay, okay. Correct.
Right. Sorry for the confusion. Yeah.
No,
At the very last step.
no. You said it properly. I just got confused. Yeah. Okay. Okay.
Yeah.
Good.
Yeah. Okay. Yeah. Okay. Good. So now that we have talked about Haitian, let's see how far we can push it. So there's this, as I said, there's another nice polynomial, the sum product polynomial, which is defined like this: is the sum of monomials like this, x11, x12, x1d, right? And they're disjoint. All the variables are totally disjoint. Right? And notice that any depth-3 circuit is in the affine projections of this sum product polynomial, because you just replace the variables by arbitrary affine forms, you get a depth-3 circuit, right? And also notice that it is also connected to the quadratic form equivalence problem. And that's because any quadratic form over C that has again n essential variables, if n is even, then that's equivalent to the second sum product polynomial. That means the sum product polynomial of degree 2, right? It's equivalent to this. So the power symmetric polynomials and the sum product.
And then we've lost your voice again.
His video also froze. So we're
His
completely.
video froze. Oh, okay, correct.
Hello?
Now no, we lost you.
Yeah. So there's some connection issue here. Let me.
Yeah. No, you were talking about the last bullet point that is there.
Right. I'm just switching to a different connection. So
okay. Sorry. No.
Yeah. Right. So as they get connected, let me keep talking. That so now the question is, can we do equivalence test for some product power symmetry? Right. So is my screen visible now?
Yes. Now it is visible. Yes.
All right. Okay. So the problem now following, given access to f, which is in the orbit of the sum product polynomial, can we recover a, the transformation a, right? N again here is s times t, because there are s monomials, each having d variables. It turns out that exactly the same algorithm that worked for power symmetry polynomial works here. Same. Why is that? Again, we have to argue the correctness of the third step. Is it true that here too the Haitian will factorize into powers of linear forms, the linear forms that we're trying to find? Yeah, it turns out that it does, right? That's because if you look at the Haitian of the sum product polynomial, now just imagine how the Haitian would look like. It would look like a block diagonal matrix, right? Each block would be the Haitian of the corresponding ith monomial, right? So I'm denoting the ith monomial by hi, right? So we need to understand the determinant of this Haitian, we need to understand how a Haitian of a monomial looks like. Fortunately, it turns out that Haitian determinant of a monomial is again a monomial. It's basically the same monomial raised to the power d minus 2. I'm not giving a proof of this, but the proof is not that difficult to work out. Yeah. So, and because of this, if you look at the overall Haitian, the overall Haitian will now again look like sums of products or sums of powers of the linear forms L11 to LST, right? So, and again you factorize and get access to the linear forms, and from this point the argument is the same as that of power symmetry polynomial. All right, so sounds good. But now that we are into this Haitian business, let's please ask ourselves, like, we can get a little optimistic at this point and notice that the sum product polynomial is actually a read-once formula, right? It's a depth 2 read-once formula, because you can write it as a plus gate on top, and then below that product gates, and the product gates take as inputs these distinct variables, right? So it's a read once formula, and let's ask this question: can we solve polynomial equivalence problem for general read once formula? So what does that mean? I'll come in a moment, but also notice that the power symmetric polynomial itself is almost like a read once formula, right? It's, except that the variables are now replaced by powers of variables, right? So they're morally read once formulas, let me put it like this. So the question makes sense, and it turns out that you can push this strategy and solve the problem for general read once formulas, right? So given black box access to F and G, where both F and G are in the orbits of some read once formulas which you don't know, and you want to check whether they are equivalent or not, and you can do this in randomized polynomial time and also find a witness A. And it's basically, you know, analyzing the Haitian matrix and how the determinant looks like for a general RF. And notice one thing, that in the sum product case, G was known. G was the sum product polynomial. But in this case, both F and G are unknown. Like you are given black box access to just F and G. All right. So you can also view this generalization as a generalization of quadratic form equivalence. Because, you know, quadratic form equivalence, because of the canonical forms, is can be viewed as a special case of read once formula polynomial equivalence, right? Okay, so with this, I'll stop with the, you know, Haitian method. And
sorry, so what happens if you had some variables appearing in two of those monomials?
Then it becomes, yeah, then it becomes read twice, right?
Correct. Yeah, that's what. So if it is not read once, but I mean, it is still some product, but
right. So correct. So read twice formulas doing isomorphism testing, I think it is known to be hard. I think at least as hard as GI. I think there's a result which shows like, yeah, for if you increase the read twice, then doing even isomorphism is a special case of equivalence where you want to check whether there exist a permutations of the variables that takes one formula to the other, right? Mm-hmm. I think that's known that is GI hard. I might be mistaken, but I vaguely recall that the result shows hardness of this problem.
Okay.
All right. So I must mention one result in this context before we go back to our mainstream, which is learning depth repowering circuit, is a result that can solve the decision version of polynomial equivalence for the power symmetric polynomials without doing polynomial factorization. And they can do it for complex numbers over complex numbers. So one appealing feature of this algorithm is that it involves only arithmetic operations like addition, multiplications, and equality tests. And it is not known whether you can do polynomial factorization using only arithmetic operations, right? So for example, if your F has rational coefficients and you want to check whether F is equivalent to the power symmetric polynomial over complex numbers, you can solve the decision versions in polynomial time, truly in polynomial time. The complexity would be polynomial bit complexity. Right. So with this, let me go back to the mainstream. Let me go back to learning random powering, depth repowering circuit, right? And ask ourselves, okay, now that we solved the S less than n case, can we solve, can we push it further? Does the Haitian help in solving the average case learning problem for S larger than n? It turns out you can do, to some extent you can do, for S up to n squared. There's a result which sort of work with even more general versions of the Haitians, what are called fourth order Haitians, where you are taking fourth order derivative. Your rows are labeled by a couple of variables, your columns are also labeled by a couple of variables, and the corresponding entry is fourth order derivative, right? So by analyzing such Haitian, this result has been shown that you can reconstruct random depth repowering circuit for S up to n squared. But it's not clear whether you can keep doing this and maybe continue to analyze higher and higher order Haitians, and maybe can you push S much larger than n squared. That's not clear. And seems like we need a different strategy at this point. And that's the second half of this talk. I don't think I have too much time, so I'll skip certain parts while keeping the focus on the main parts. All right, so now again, just to summarize, at the end of the first half, we solved the average case step 3 parting learning for s less than n, and now we want to do it for s much larger than n. Right? And the question is, can we do it? Right? And in this half, I'm going to talk about a strategy, a framework where we can design average case learning algorithms from existing lower bounds, known lower bounds. So recall that in the first part, we mentioned this result that showed that learning is strictly harder than, not strictly, it's harder than lower bounds. It's not known to be strictly harder, but there are indications that it is actually strictly harder. It is an inherently hard problem, right? So, but now the question is, does existing lower bound help in designing average case learning algorithms, right? So to see this, let's see how a typical lower bound proof looks like, right? So let's say I have a circuit class C, and the polynomials, you can think of C as a depth 3 powering circuit for convenience. Right? The polynomial f can be written as a sum of simple polynomials t1 through ts. For example, in case of depth 3 powering circuits, these simple polynomials ti's are powers of linear polynomials. Right? So they are simple in some sense. Right? So, and the way a typical lower bound proof goes is by defining a map, which we call complexity measure. It's a map from the ring of polynomials to natural numbers that satisfies these 3 properties. That it is subadditive, that means mu of f plus g is less than mu of f plus mu of g. And mu of a term, which is a simple polynomial, is somewhat low, somewhat small. And mu of some explicit polynomial f, let's say determinant or something, is high, right? And if you know this, then you immediately get a lower bound, right? From the subadditive property and from the structure of f, if you apply mu on both sides, you know that mu f is larger than h, whereas mu of each term is smaller than t, and use the subadditive property to then show that the number of terms s that you would need is larger than h by l. That's how many lower bound proofs look like. Okay, but there is more to the story, that it is not just these complexity measures, but the origin of this complexity measure. It turns out that these measures in these proofs are actually dimensions of vector spaces that are associated with the polynomial f and the terms. Yes. Right? So let's go further, dig deeper, and see how these vector spaces come up by looking at, again, depth 3 powering circuit. Right? So depth 3 powering circuit looks like this, and the lower bound for depth 3 powering circuit, it looks at define this notation. This partial k means the kth order derivatives of f, right? And u be the space spanned by the kth order partials of f, right? And ui be the space spanned by the kth order partials of the terms. And mu of f is defined as the dimension of u. So this is the vector space that we were alluding to in the last slide. Yeah. Notice that by definition, because partial order derivatives are linear operators, we have u contained in u1 plus u2 to uf, right? Which means that we automatically get the subadditive property, that the dimension of f must be smaller than equal to the sum of the dimensions of the ui's, right? So, right. So, and just to complete the lower bound proof, although not strictly speaking not required, just to complete the lower bound proof, you see the way we have defined the partials, the mu measured here, mu of a term is 1, right? Because it's a power of a linear form. If you take derivatives, you get basically a scaling factor times, again, another power of the same linear form. So mu of a term is 1, whereas mu of this monomial, x1 through xn, is n choose k, because you can take all possible kth order derivatives of this monomial and you get different monomials. And that immediately gives you a lower bound. If you choose k to be n by 2, that immediately tells you by subadditivity that your S must be at least like 2 power n or so, right? So that's how a lower bound looks like. But let's get back to this property, right? And let's just summarize and into this slide that a typical lower bound proof for a complexity class C involves not just a complexity measure, but within that there is a set of linear operators. Yeah, let's denote it by this calligraphic L. Linear operators on a ring of polynomials, such that the dimensions of the space spanned by the linear operators applied on Ti is small. Right? For example, this linear operators in case of the depth 3 powering circuit case was just the kth order derivatives. Right. So if you apply it on F, and it right? Yeah. Any question? Any question? Sorry.
No. Again, you're briefly this thing. Yeah, but it's okay.
Okay.
Yes.
Okay.
No
Okay. Right. Am I audible now?
Yes. Now you're completely audible. Yeah.
Okay. And this relation that you see here, this is the origin of the framework that I'm going to state now. At this point, notice one thing. So far, we did not talk about random terms, right? We know a typical lower bound proof gives me a set of linear operators. I can attach spaces like this. Now, the hope is if the terms are random, then we can expect a couple of things. First, that the sum of the spaces is actually a direct sum. And second, that containment that you see here, the hope originates from the fact that the dimension of the spaces for a term is small, right? And the terms are random. So if the linear operators are nicely behaved, then one would expect this kind of things, right? But at this point, it is just a naive hope, right? I don't have any evidence to support this at this point, right? So we expect that this space at the left-hand side decomposes into subspaces, and this decomposition is given by this direction, right? And this immediately gives us a crude approach, first approach to a learning average case lambda. What do? I have F, right? I'm ignoring black box access for the timing, so you can ignore that. It's just a crude approach, right? So first you compute this space, yeah, the space associated with F. Yeah, L is a known set of linear operators. For example, L can be just the kth order partial derivatives for some reasonable value of k. Then you decompose this space attached with F into subspaces. The subspace, hopefully the subspaces attached with these terms, and finally derive the terms from these subspaces. This is a very crude high-level approach, right? But does it make sense? Even at the high level, you see it doesn't make sense immediately. Why? Because when I say decompose a vector space into subspaces, what do I mean by this? A vector space can always be decomposed as a direct sum of its basis elements, right? So some basis elements. What is so special about these subspaces? Only if I tell you that, okay, something is special about these subspaces, that I can hope to decompose it into these subspaces, right? So let's see why they're special. It turns out that a typical lower bound proof has more to it. In their linear operators that we saw, L, they can be expressed as a composition of two sets of linear operators. Just to give an example, we saw this kth order derivatives, right? You can always write a k plus 1th order derivative as a composition of a first order derivative and a kth order derivative. So in that sense, I mean, typically the linear operators that we see in lower bound proofs, they can be decomposed very naturally into two sets of linear operators, L1 and L2. Yeah. So now with that, let me come back and say, refine our expectation, right? So now we expect that when the terms are random, then when you apply the first linear operator on F, the corresponding spaces that you get, they should decompose like this, and you get an equality and a direction structure. And then when you apply L2 on the first spaces, right, then you get L, right? When you apply L2 on the first space L1F, you get L, right? Because L2 composed L1 is L, right? So, and sorry.
Sorry, no. My Siri suddenly took off. Sorry.
Okay, right. So just to refine that expectation, that we do expect that that there are two vector spaces, and both of them decompose like that into smaller subspaces, right? So let's simplify the notation a little bit for subsequent slides. Let me call the first space here U, and the component spaces here as U1 through US, and the second space here as V, and the component subspaces as V1 through VS. Right. So with this notation, I switch to this slightly more concise, succinct notation that U decomposes like this, V decomposes like this, under the action of L2. L2 takes, notice that L2 is what is taking U to V and U1 to V1 and so on, US to VS. Right. So at this point, I think we are sort of ready to say why we expect the component subspaces to be special. It is because of the action of L2, right? So we can further expect at this point that the above decomposition is unique. Above decomposition of U and V is into subspaces, indecomposable subspaces, is unique in the sense that that L2 is taking UI to VI, right? Among all decompositions, I can expect that if I start with some arbitrary basis elements, this may not happen, right? So what this is saying is, if you, so it is basically saying with respect to a certain nice choice of basis, you can write the L2 operators as block diagonal matrix, right? But you may not be able to write the L2 operators as block diagonal matrices if you choose arbitrary basis elements, right? So that's the point, right? So and the L2 is what is attaching some sort of uniqueness to this decomposition, right? So I hope this is okay. And just for brevity, I will the third expectation, I will just write it like this, that we do expect that this decomposition is unique under the action of L2, right? So and now we are in a position to state a refined meta algorithm, keeping in mind that L decomposes as L1 and L2. Right? You first compute basis of U and basis of V. Then you decompose U and V under the action of L2. Right? Into this, you will get U1 through US and V1 through VS. And now you obtain your terms from the UIs. Right? Recall the UIs was just L1 applied on TI, right? So, but although it's easy to state, we'll see in subsequent slides, there are a few technical challenges. I'll just mention them, right? So what this meta algorithm does at a high level, it reduces the learning problem to a vector space decomposition problem. And the reason it is able to do is because of those linear operators L, which originated from lower bound proofs. Right? So that's why, like we can call it, you can view it as learning from lower bounds. Right? Okay, so as I said, like there are some technical challenges. Let me quickly mention those. The first one, of course, is as I say, like we expect that U should decompose as U1 through US and V should decompose as V1 through VS. But we have to show this. We have to show that if we choose T1 through TS randomly, then indeed they decompose as like this, with respect to the operators L with high probability. So that's the first technical challenge. The second technical challenge is the third expectation. We need to show uniqueness, that this is the only way you can decompose when you choose T1 through TS randomly under the action of the L2 operators, right? And it turns out that the algorithms that have implemented this strategy, in those algorithms, the main action takes place basically in task 1 and task 2. So most of the effort goes into those algorithms, right? And And just to summarize, task 1 and task 2 is just basically showing that a random circuit, by a random circuit, I mean the terms are chosen randomly. You can always keep the depth 3 powering circuit in mind, where the coefficients of the linear forms are chosen randomly. Right? I want to show that they satisfy direct sum and uniqueness criteria with high probability. And if they do satisfy, then I'm going to call them as non-degenerate depth 3 powering circuit. The remaining 2 tasks are relatively easy, I would say. Task 3 is, once you have shown uniqueness, now what remains is to decompose U and V under the action of L2. Yeah, there are standard intensely in the 80s or so, and there are, I'll mention in the following few slides that there are standard algorithms known to solve task 3. And task 4 finally is to recover the UIs, and again, at times they can be a little non-trivial, but they're usually, especially when the operators are just derivatives, partial derivatives, they're very fairly standard. Like this basically says, like, from the derivatives of f or a term, can I recover the term, right? And there are Lagrange formula or something which you can use to recover the terms from the derivative. So let's keep our focus on task 1 and task 2. I'll just talk about a little bit about yes.
So like, for example, like the example that you've given for like powering, depth 3 powering.
Right.
So if you take S is less than equal to n, then with high probability you're going to have statement 1 with.
That's right.
So that means like, instead of subjectivity you have additivity for the measure of partial derivatives, is it?
Right. So you're talking about the equivalence case, right? So where
yeah,
all the linear forms are linearly independent. Correct. In that case,
the same strategy works here as well. If you have depth 3 powering circuit,
that's correct. That's correct. It holds true. But the point here is, here you can allow S to be much larger than n, and you will still get the direct sum and the equality with high probability. So the linear forms will no longer be linearly independent. They can't be, right? Because there are n variables and you have much larger number of linear forms. Although the linear forms are not independent, but the powers of the linear forms can be independent, right? So that's the point here, because I'm working with high powers of linear forms. So they can still be independent.
And what will the uniqueness be here?
Uniqueness, yeah, I'll come to that. I'll come to that. So I'll elaborate a little more on this task. But by uniqueness, I mean that the decomposition that you see above, that U must decompose into U1 through US, V must decompose into V1 through VS under the action of L. Again, under the action of L, I mean basically satisfying this criteria, right? Can I get another bunch of UIs and VIs such that the last line that is written here, that VI should be would be equal to the space spanned by the L2s acting on the UIs? Can this happen for another bunch of UIs and VIs, right? So that if it happens, then I would, we would be in trouble, right? So we wouldn't know that the UIs are the UIs that we wish to recover. Right? What are the UIs again? The UIs, here they are derived by operating on the actual terms. So yeah, so the UIs are the relevant. I am not interested in any other kind of UI primes. So we need to show uniqueness.
Okay, thanks.
And what are the L1 and L2 you use? They're
okay.
derivatives.
So before I elaborate, right, so depth 3 powering case, you can just use L1 as the kth order derivatives and L2 as just a single order derivative.
Okay.
Just first order derivative. Yeah. Okay. Right. So quickly, I just want to mention this, that there have been works that implemented this strategy. Actually, the first one introduced this framework, but in a rudimentary form. But what they were able to show is they could come up with proper learning algorithms for random depth 3 powering circuits, where S is nearly as high as the best lower bound, like n to the d. for example, if you choose D to be like N, you get 2 to the N, right? And recall the lower bound that we showed for depth-free powering circuit computing a monomial is 2 to the N, right? So it's much larger than N squared that you could, that currently we know of doing using the Haitian. And we know more, we can push the model further. Instead of depth-free powering circuit, which is sums of powers of linear forms, we can look at sums of powers of quadratic forms or degree 3 forms or degree 4 forms. And still you can apply this framework and learn such circuits. It turns out, to our pleasant surprise, it turned out that the t equal to 2 case has some potential nice applications in learning. This is called another problem, mixtures of Gaussians, which is quite popular in machine learning. So let me not go into that, but I'm saying potential applications because there are some hiccups on the way. Okay, so and there's a third work which sort of generalized the first work by instead of depth-free powering circuit and general depth-free circuits, they could handle generalized depth-free circuits. So let me just mention at least what a generalized depth-free circuit is. So in a depth-free circuit, we will have products of linear forms, right? You can think of the GIs as just a monomial there, right? But in a generalized depth-free circuit, these GIs could be anything arbitrary, like can be a determinant, can be IMM, or even random GIs, right? So what this work showed is if these GIs come from well-defined polynomial families like elementary symmetric polynomials or determinant IMM or monomials, which is the depth-free case, then you can learn such circuits in the average case. Or if the GIs are randomly chosen, then also you can learn. But more interestingly, in this work, they give a slightly general way to accomplish, and a methodical way to accomplish task one. So let me not go into that. Because I don't have too much time.
Yeah, so it's but I'm sure you can take 10 minutes. It's officially 5 minutes.
Okay, great. 10 minutes.
Yeah.
Okay. Yeah, sorry about it again. So, okay, 10 minutes is good too. Right. To elaborate on the first part, just let me go to the examples right away. That what this means for a depth-free powering circuit is to show that the kth order derivative space splits into the product of the kth order derivative spaces attached to Li's power D's, which are basically one-dimensional spaces, right? Right, for example, let's focus on the direct sum. Yeah, what does it take to show that if I choose the Li's randomly, this direct sum holds? The direct sum here, because they are one-dimensional spaces, means that they should be linearly independent. We have to show linearly independent. And in this case, it turns out to be easy. Like it's not too hard to show. Like if you choose random coefficients, then and choose the powers, the point is D minus K can be large, right? And then such linear forms are independent with high probability. Right? So this turns out to be fairly easy for depth-free powering circuit, but can be potentially non-trivial. For example, turned out to be non-trivial for the depth 4 circuit case. And so, so I wanted to touch upon only task 2 because this is conceptually more interesting than the other steps. Task 2 is the uniqueness part. I want to show uniqueness of U1 through this split, U1 through US. How do I do this? Now, there is a very nice handle to it. It's called the adjoint algebra. So let me just define it and tell you why it plays a crucial role in the analysis. The adjoint algebra is an object which is associated with this triple U, V, and L2. L2 is acting on U and taking U to V, right? And it is a set of tuples, which are maps, linear maps, phi and psi. Phi is a linear map from U to U. Psi is a linear map from V to V. You can think of them as matrices also, such that the following relationship holds. Right? If you pick any operator, lambda from L2, then lambda composed with phi will be equal to psi composed with lambda. If this holds, then you put such tuples phi and chi in this set adjoint UVL2, right? So just notice this map lambda composed with phi is a map from U to V, right? Because phi is a map from U to U, and lambda by definition is an operator in L2, which operates from U to V. Similarly, chi composed with lambda is also a map from U to V, because lambda takes U to V, and chi is a map from V to V. What this definition is saying that if these two maps are the same, then I put phi and chi in this adjoint. Yeah, so that's the thing. Let me skip this. The interesting part is that this adjoint phi and chi gives rise to several other decompositions, potentially several other decompositions of U. In fact, one can show that U also decomposes as phi U1 to phi US, chi V1 to chi US, and that also is a valid decomposition because L2 operating on phi will take you to chi V1, right? L2 operating on phi UI will take you to chi VI, right? So if this is giving rise to several other decompositions, to show uniqueness, we must pay some attention to this object, right? And it becomes absolutely necessary, let me skip the proof, because of a very well-known theorem which says that this is the only way U and V can decompose under the action of L2. Adjoint is the only way where phi and chi are inverted. So it becomes necessary to understand this object, these linear maps, phi and chi. And so how do we show uniqueness? And it turns out, let me just state the thing. Okay, let me just state it without proving that there is a nice sufficient condition. If we prove that sufficient condition, then that will imply uniqueness. So let me just state the sufficient condition. First, observe, let me define phi I as a projection map from U to UI. Right? It takes the vectors in U and projects it to just the UI component. Similarly, chi I is defined as a projection map from V to VI. It turns out that these tuples, phi I, chi i's, one can show, all the proofs are given in the slides. I'm just skipping them. They're actually these short, like 2-line, 3-line proofs. Right? So it turns out that these tuples, these projection maps are in the adjoint. And we say that the adjoint is trivial if the adjoint is generated as a vector space by these projection maps, phi I, chi. Now comes the important claim that if the adjoint is trivial, then one can show the uniqueness that we want, that U indeed decomposes as U1 through US, and this is the only decomposition. Yeah, and V decomposes like this under the action of L2. Right? Again, the proof is given in the slide. This time the proof is just one slide, not 3 lines, but it's fairly easy. I'm skipping it here. Yeah, and so what these papers do is they actually show that the corresponding adjoint algebra is trivial, and that implies uniqueness of decomposition. And once we get uniqueness, we are done. We apply standard vector space decomposition algorithms. There are several standard ones known over finite fields, complex numbers, and also over rationals. Somehow we are able to do some certain things, again using the adjoint, to make sure that it works even over rationals. So the results that we stated, it also works over rationals, not just things. All right, so this brings me to the last step. Let me skip the last step because it's fairly simple, but not necessarily simple always. Like the last step of recovering the terms from the UIs, sometimes it becomes slightly complex, as in the depth-4 case. But I would like to again bring your focus to just step 2. Step 2 is basically, and step 1 along with it, the heart of this framework lies in those 2 steps. Once someone shows that a random circuit satisfies the step, task 1 and task 2, then the rest of the things becomes fairly easy. Yeah, so there are other average case learning algorithms that don't follow this framework. For example, there's a result which proper learns random fan into multilinear formulas, and similarly learning random fan into regular formulas. So regular formulas are formulas where all the nodes at a level have the same fan-in, right? Fan into means like throughout the formula, so it's like a complete binary tree. Right? Similarly, there is a result which can reconstruct random ABPs, but those ABPs must have low width. Yeah. Okay. So all these algorithms, although they don't state it explicitly, they're implicitly connected to certain, the lower bounds. And I must say that lower bounds for whatever models, multilinear formulas, regular formulas, ABPs with lower bounds, learning is for a model for which lower bounds are not known. So far it turned out to be like, for whatever models we know of learning and even average case learning, even they have existing good lower bounds. So I would end with this question here: can we implement this framework for other circuit models, right? For example, like here, there's this slightly small thing that they could reconstruct, but they crucially need the fan-in too, especially in this result. Their formula needs fan-in too, and the proof strategy, it's not too clear. It becomes difficult to adapt the strategy to higher fan-in formulas. Whereas vector space decomposition, by definition, it doesn't care about the fan-in, right? As long as the fan-in is not too large, right? So it can decompose into component spaces and try to retrieve the terms from the spaces. So there is a chance that this strategy can help in reconstructing more powerful circuit models like constant depth set multilinear circuits or general regular formulas, right? So for all these models, good lower bounds are known. Right. So just to summarize, in this talk, we basically kept our focus on two things: the polynomial equivalence problems and average case reconstruction, that too on a particular framework on how to do average case learning from lower bound proofs, right? And in the polynomial equivalence problem, we focused on Haitian-based arguments, right? And in the average case learning algorithm, we focused on this approach that reduces learning to a vector space decomposition problem. Okay, that's it. Let me end my talk here. Thank you so much.
Thanks, Chandan. Thanks.